Hello, my name is Ashton Woods. I'm a geologist with the United States Geological Survey at the Earthquake Science Center in Menlo Park, California, and I am very pleased to continue the Climate Change Impacts on Natural Hazards lecture series part 2. Please give me a moment to share my screen and we will get started with the lecture. Thank you. Lecture 19, Climate and Hazards Part 2 from the Climate Change Impacts on Natural Hazards series. Let's do a quick recap. Greenhouse gases were a large contributor to atmospheric changes, climate change variations, and natural disaster generation. Several different indicators were pollution, storm intensity, unpredictable weather, seasonal variations, droughts, and crop failures. Indonesia is particularly vulnerable as it only has a rank of 97 on the INDIGAIN index dealing with climate resiliency and disaster preparation. There are some noticeable trends that have occurred throughout Earth's history on variations in climate. We see these trends through investigation of the paleoclimate of the Holocene as our current climate is reaching a similar climatic optimum seen 5,000 years ago. Samoa is WSM on this chart and is more susceptible to disaster impacts and climate change variations than Indonesia on the INDIGAIN index. Japan has a lower rank of 15 and has enough funding for the implementation of mitigation tactics that improve their readiness rating for climate and disaster impact than Indonesia or Samoa. Indonesia requires improvement to disaster mitigation techniques and should include policies on climate change during the mitigation process so that Indonesia can reduce their vulnerability rating. So now let's continue to part 2 of climate change impacts on natural hazards by focusing more on the impacts of drought conditions with surface changes that contribute to seasonal variations of rainfall and an increase in disaster frequency and intensity. It's important to look into this as seismic activity can cause an increase in landslide and debris flows during drought-like conditions. This is because the surface is incapable of withstanding energy changes within the lithosphere due to lack of sediment stabilization and nutrient leaching that occurs when moisture is lost in the soil from evaporation. These inelastic soils can undergo what is known as soil amplification, where the surface mimics the wave energy. Additional disaster events such as mud flows and flooding can also increase in frequency by introducing heavy rainfall following drought-prone areas or due to tsunamigenic waves over drought-prone soils. Flooding becomes increasingly devastating in areas where soil drought conditions have occurred. This 2018 model that you see on the right-hand side investigates in the soil drought trends in Indonesia. The drought severity level may appear rather low, yet 80% of Indonesia is identified as experiencing vulnerability to drought-prone surface changes due to atmospheric and environmental consequences. We are aware that one of these atmospheric and environmental consequences is the exposure of fire activity in tropical swamplands that contribute to the greenhouse gas emissions that we mentioned in Climate Change and Natural Hazards Part 1. It is also important to note that the consequences of peatland fires are not solely responsible for the development of prolonged soil drought conditions in Indonesia. The anthropogenic interference of industrialization and urbanization in densely populated areas of Indonesia causes significant water stress to happen above and below the surface level, resulting in soil moisture variations. The overuse of these water resources, whether they be surface or subsurface, also cause changes in available water known as water scarcity. Water scarcity is the lack of available fresh water to meet the demand of the affected population in areas where water stress is present. Water stress and water scarce cities present difficulties when attempting to properly handle natural disaster events, as funding for mitigation tactics focus less on natural hazards and disasters and more on increasing the water supply, which can result in man-made channels or installments of new wells. These types of mitigation tactics can cause an increase to vulnerability of seismic and flooding-related disasters. It is important to understand the water capacity of underground aquifers and terrestrial water resources to be able to properly investigate and mitigate against potential natural disasters that are influenced by these changes. We can examine the change in water capacity by researching surface anomalies of terrestrial waters. Here I have one of two examples from GRACE satellite data that show the surface anomalies for terrestrial waters for the months of May and June 2020. The units are in meters of equivalent water height and looks into the measurement of the water column based off of gravitational anomalies and subsurface density changes that can be recorded by the GRACE satellite. Indonesia is on a relatively higher level of EWH than, say, Malaysia to the north. This would suggest that there is plenty of water that's still existing on the surface, but has little drainage, allowing for potential floodwaters to impact the surrounding environment. Now reviewing June 2020, we can see that there are certain parts of Indonesia where the equivalent water height of the water column has extended, especially over North Sumatra and Borneo. The sudden change within a month could be an indication of heavy rainfall where the water has had no outlet to go, and so there is more infiltration and subsurface runoff that's causing these surface mass anomalies to occur. The sudden change between drought conditions and flooding events were particularly damaging in the Kalimantan areas of the island of Borneo for the month of June 2020, as the dry seasons resulted in several fires and sudden rainfall caused significant sediment transport during the flash flood events. So let's investigate these surface mass anomalies further to understand the subsurface conditions for Indonesia. This data is from 2020 and shows the vulnerability of groundwater resulting into groundwater stress, particularly around the densely populated cities of Indonesia. Understanding subsurface changes in groundwater allows us to understand the water column and surface changes surrounding different rivers and water reservoirs on the surface, as well as understanding how seismicity following wet dry season variations can occur on surface and subsurface areas, resulting in aquifer collapse or liquefaction events. Here we see a seismicity hazard map that is not tracking an energy or magnitude of the earthquake, but is instead looking into the PGA, or peak ground acceleration. Peak ground acceleration calculates mass acceleration during the time of seismicity that contributes to ground displacement and soil amplification. When we compare the seismic hazard map to the previous map for groundwater stress, it is curious to see that the 2018 data, represented in blue, correlates with the data on the seismic hazard map, represented in blue and green, along the alluvial plains of the main islands in 2020. Investigation into hazard maps within a 5 to 10 year period can help us recognize reasons why natural hazards will present and how significant a natural disaster can be in exposed or vulnerable areas. It also allows emergency planners and geologists to understand why surface changes are occurring and whether it is because of slow processes like erosion and weathering, or due to fast processes that are either naturally or anthropogenically caused. With the majority of Indonesian population at risk of rising sea level and from sinking cities, investigating surface changes in relation to climate variation and from disaster events can motivate the government and private sectors to consider the development of new mitigation tactics suitable to the hazards present within the area instead of simply adopting a one-fits-all mitigation solution. Accommodating to unique hazard situations can build disaster resiliency over time. I would now like to play a video on surface runoff and how sediment transport plays a role in surface changes following heavy rainfall.
I'm Jim Johnson. I'm a senior soils and crops consultant here at Noble Research Institute. Today we're going to be demonstrating our rainfall simulator. The soil in each one of these trays is the same soil type. These were all taken from within a quarter of a mile of each other on the same soil type. Our first tray has no soil, it's just our check. Our second tray is bare soil that's had heavy tillage, lots of disking, lots of plowing, lots of rototilling, lots of tillage on this and no crop growing. Our third tray has wheat growing in it. It has been tilled occasionally over the past several years and it has had some crop rotation. So it's had some wheat, it's had some beans, it's had various crops growing on it for the past several years. Our next tray is also wheat. It is no-till, so it has not been tilled in any way for years and years. It's planted with a no-till drill, so we just plant the seed directly into the soil without doing any tillage. It's had cover crops on it during the summer and the winter for the past several years. Lots of diversity in plants. And then our last tray is some native grass. It's got some little blue stem and some Indian grass in it. Native pasture, no grazing, but just managed as a native pasture. None of these have any livestock grazing on them. So let's turn it on and see what happens. So our first pan was our check. Obviously no runoff in the front. Everything filled the jar that would have been what soaked through this pan. It just simply went through the bottom of the holes in the pan and came out the bottom. And this gives us an idea of what that water would look like with nothing there. Nice and clean water, no silt, no soil, just all the water that went directly through and into our jar. For our clean-tilled, heavy-tilled soil with no crop on it, there's almost no water that soaked into the soil and came out the bottom. There's just a little tiny bit of dirty water in the bottom of the jar that caught what went through the soil and out the bottom. Almost all of the water on our clean-tilled, no-crop soil ran off the surface and into this jar. So when we have bare soil that's uncovered and has been disturbed with lots of tillage, we can have lots of runoff that takes the surface soil with it. Unfortunately, that topsoil is our richest soil. It's also where we typically apply our fertilizers to grow our crops. So when the water in the soil runs off, not only does it take soil with it, it's taking those fertilizers that we applied to grow our crops with it as well. Those eventually can end up downstream in our rivers and our lakes. In our field that has had some crop rotation and some tillage, we see we had some runoff. It's cleaner than our field that had heavy tillage and no crop, but we still have a little bit of silt in the water, some that ran off, but we had quite a bit that soaked in as well. It's a little bit silty, but not too bad. That's to be expected when it runs through the soil profile, through the soil, and into what would be our aquifer, or into the water table, into the soil water that we store. In our field that had had several years of cover crops and no tillage, we see that every bit of the rain that fell soaked into the soil and ran through the soil profile. There's very little water that ran off, and the water that did run off is very clean. That's because this soil is healthy. It's had healthy crops growing on it. It hasn't been disturbed with tillage. All of our soil and nutrients are staying place in the field, and all of the rain that falls is also staying in that soil profile to grow a future crop. Our final field, our final pan, is our perennial grass, perennial warm season grass. Every bit of the rain that fell on this field soaked into the soil. There's no runoff, zero surface runoff from our well-managed native perennial grass. Good cover on the soil, no nutrients leaving the soil, no soil leaving the field. All of our water is soaking into our soil profile and will be there to grow that grass for us during the dry season. I think an important takeaway from this simulation is the amount of runoff that we have from our disturbed soil sites versus the lack of runoff from our sites, whether they're cropland or grassland, that are managed using the soil health principles. Our two pans on the end have had the soil covered. We've minimized disturbance. We've had no physical disturbance in the grass, and we've planted with no-till in the wheat field. We've increased plant diversity. Obviously, a native pasture has a diversity of plants. While we're only growing wheat at this time, it's had a great diversity of cover crops grown on it. And we've kept living roots in the ground. Obviously, our native grass will have warm and cool season plants in it, so there's always actively growing roots. And in our cropland field, we've kept warm season and cool season crops on it to keep actively growing roots in the ground all year long. On the other hand, if we have soil disturbance, we have less plant diversity, obviously no roots in the soil in our bare ground, no cover on our bare ground. We can see what happens by not following those soil health principles, and we have water runoff and silt runoff.
The diagram on this page is to be utilized as supplemental material to the simulation that explored into infiltration and runoff rates based on vegetation and soil complexity during heavy rainfall. Here we see that number 1 is a no vegetation over-tilled soil where the majority of the water all resulted in purely runoff. And then number 4 being the opposite of the spectrum, filled with natural vegetation and no tillage, showing that the groundwater was able to withstand all of the water from the heavy rainfall event with limited amounts of runoff. This isn't entirely true during areas where soil saturation occurs, as the amount of groundwater in this area can cause the water to continue rising due to gravitational forces and end up on the surface, to which it'll end up as runoff during flash flooding events. However, for the purpose of the simulation, this isn't during a flood-related disaster. This is simply just revealing how different types of soil and vegetation help to prevent runoff or can cause runoff based off of heavy rain events. Now we'll look at the map that shows a ranking of countries 1 through 10 that are vulnerable to erosion of watershed areas and are represented in green. 1 represents the highest risk of erosion and 10 represents the least risk. Indonesia is listed as number 3, 5, and 8 on this map and includes the islands of Java, Timor, Sulawesi, Palu, and East Indonesia. The erosional forces on watersheds following disasters and heavy rainfall events causes sediment to transport towards the coastline, and these sediments can often be contaminated by other chemical toxins, pollutants, or an abundance of nutrients from leaching. When toxins, pollutants, and nutrients are introduced into the marine and coastal lagoons, eutrophication can occur. Eutrophication is the pollutant or nutrient overload that is responsible for causing turbidity and environmental issues in areas that are unable to filter out these pollutants and nutrients naturally. It is a driver for harmful algae blooms that contribute to atmospheric anomalies and is directly influenced by climate variations of wet and dry seasons. I won't go too far into the science of harmful algal blooms, but it is important to acknowledge that these HABs are a climate consequence that can occur following inundation-related disasters or during unpredictable wet and dry season variations. Harmful algal blooms are an additional source of greenhouse gas emission and can occur in freshwater lakes, lagoons, or in marine waters. HABs are also responsible for inducing hypoxic conditions and limiting the amount of sunlight that can penetrate through the water. This diagram shows that there is methane and CO2 production that can occur from harmful algal blooms during the decaying process. Also shows that sunlight essentially scatters across the harmful algal bloom and is unable to infiltrate past the water surface. The lack of light penetration and the oxygen that is being depleted from the decaying algae creates the hypoxic zones. Excuse me. These hypoxic zones damage natural barriers from terrestrial and coastal environments and diminish the survivability of the ecosystem with the marine and freshwater environments. There are 2 different examples of blue-green algae responsible for harmful algal blooms. Mentioned in this diagram, cyanobacteria is one such one, and the other one is trichodesmium. Cyanobacteria is potentially the worst of these 2, as it can not only cause damage to marine and terrestrial water bodies and their surrounding ecosystem, but can also cause significant obstruction of health in people and animals that get too close to the algal blooms when they occur. These harmful algal blooms can be responsible for changes in coastal and lagoon areas due to destruction of natural barriers that help to diminish the impact of tsunami, high tide, and flash flooding events, and it can also influence changes in sea salinity levels as well as sea surface temperature. In freshwater environments, it's capable of intensifying wet and dry season variability due to the release of CO2 and methane when the algal blooms decay. So not only are HABs a product of climate change, they can also be a driver for initiating climate variations and disaster frequency, should they be left untreated. We will transition for the moment into desertification processes to investigate further into how desertification plays a role in wet and dry seasonal variability and how desertification causes surface and subsurface changes, creating more disaster risk potential. Here in this image, we see the remnants of a palm plantation in the Kalimantan province of the island of Borneo. We see several different areas on this image that have white deposits on the surface, which is a process known as soil salinization. This is where the soils have a normal concentration of salts deposited from either natural processes or due to the introduction of fertilizers and pesticides. The salts have leached up to the surface, allowing for the lack of vegetation as the soil profile becomes uninhabitable for agricultural and agroforestry production. It is important to note in this image desertification as it is being experienced at a mass concentration across Indonesia. As these lands are undergoing the process of desertification, they become unstable and are incapable of withstanding different types of disaster events, such as heavy flooding or seismic activity, leaving it more susceptible to liquefaction events. But quickly, we will watch this video on defining information of desertification and how the United Nations has created a global initiative to combat against desertification as it is happening in various different countries across the globe.
Desertification is one of the biggest environmental challenges facing the planet. A process by which fertile land in dry regions becomes desert due to changes in the climate and human activities. According to the United Nations, over 24 billion tons of fertile soils disappear every year. 2/3 of the Earth is today in the process of becoming desert. If we don't do anything by 2050, 1.5 million square kilometers of agricultural land will be lost, an area equivalent to Peru and Ecuador combined. Indiscriminate logging, exhaustion of land by intensive farming, and overgrazing are the main causes of desertification. Extreme weather phenomena, especially drought, also reduce arable land to desert land that is of vital importance in feeding the population. This is why desertification is such a lethal phenomenon for the planet. It is contributing to the disappearance of plant and animal species, causing poverty, conflict, and the migration of millions of people across borders. It also affects the climate through the formation of hurricanes, flooding, and water pollution. But the good news is that governments have promised to fight desertification from now until 2030. Measures such as reforestation and the natural fertilization of the land to reduce evaporation, responsible planning of grazing, rotation of crops, and protection of soils from wind erosion can halt desertification and return the planet to good health.
We will now explore into additional processes that lead to desertification. Aeolian erosion is one additional process responsible for influencing vulnerability of the soil profile at surface levels. Deflation is particularly devastating for Indonesia. Deflation can move sediment several hundreds of miles away from the source of origin and can even carve out areas experiencing extreme vulnerability down to the water table. Indonesia experiences deflation in areas that have been heavily deforested. These areas are experiencing nutrient leaching and are particularly vulnerable to mud flows, landslides, debris flows, and liquefaction events following seismic activity or heavy rainfall. Erosion will occur due to lack of vegetation and lack of stability within the soil. Whether or not the soil has undergone soil compaction can greatly increase the level of ground displacement that occurs following these disaster type events. Here we see a close-up of soil salinization. As salts are being leached up to the surface, it causes the soil to become contaminated and causes an overabundance of salts to enter into the root systems of local vegetation, causing the vegetation to die off quite quickly. The sudden level of decay that occurs is capable of causing severe ground instability. Soil salinization can either happen from anthropogenic consequence of agricultural pesticides and fertilizers being leached out into the surface, or can happen during tsunami-related events. Tsunami-induced soil salinization is prominent around coastlines. The tsunami contributes to soil salinization during the actual tsunami event, where seawater infiltrates into the groundwater sources and through the mixing of brackish and saline waters into lagoons, rivers, and wetlands that are submerged during the tsunami event, shown on the figure in the image below. After the tsunami, when the waters recede out, the groundwater becomes thoroughly contaminated with saline water, and the terrestrial water bodies that were once freshwater areas have suffered the same fate, mixed thoroughly with seawater, as we see above. This causes terrestrial freshwater ecosystems to disappear within the water body. The water body can then dry up during drought conditions later in the year, and these salts within the soil start to leach its way up to the surface, causing instability in the soil for the surrounding area and causing more susceptibility following the next tsunami event, where more and more sediment will be able to be carried into coastal waters. We have covered soil salinization thoroughly for the purpose of this lecture, so now I would like to shift gears and investigate the soil compaction and its role into the desertification process. The image on the right is representative of soil moisture level averages between January to December as collected over a 20-year period. High soil moisture results in saturation to occur during wet seasons and diminishes the pores within the soil. This can cause density changes that allow for soil to undergo compaction, which creates ideal conditions for runoff potential following heavy rainfall and inundation events. This is particularly true in Indonesia, which we can see in the right-hand image where the soil moisture is particularly high. But these are high over the areas where there are tropical peatlands, so this isn't surprising. During soil droughts, however, soil moisture begins to evaporate and soil compaction begins to appear in those peatlands, allowing for runoff potential to carry away more and more sediments with each heavy rainfall event towards coastal waters. When sediments bleed out into the coastal regions, or when there are heavy flood events that carry sediments to the coastline, this process can increase sea salinity levels. Here we see a simulation of the SMAP data satellite measuring sea surface salinity between 2018 and 2019. In just a moment, we'll take a second to pause over the Pacific Ocean, showing Indonesia. Here we go. Where the sea surface salinity here is fairly low, as designated by the chart on the right-hand side, or on the right bottom side. On the next page, we'll look at the 2020 data. Here we are. Here's the 2020 data, also showing sea surface salinity, but in relation to several flooding events that happened for northern Sumatra and along the western coastline of Borneo. Here the sea surface salinity scale is changed, where purple is the lower level of sea surface salinity and the red to whites are higher levels of sea surface salinity in the same measurement of PSUs. Near the coastline of Sumatra, we see changes in the sea surface salinity from sediment bleeding out into coastal waters following a riverine flooding event, as seen here. This can also be observed on the western coastline of Borneo, where heavy rainfall caused significant sediment transport, and sediment load along the coastline following flash flooding at the beginning of August. If we look close enough, we can see the damage of the sediment, as is shown here, along the coastline, causing significant changes to the sea surface salinity and allowing for the sediment to bleed out into the coastal waters. This occurred during early part of August in 2020, as shown down below, August 1st, 2020 to August 3rd, 2020. Here we see just a few days later, August 4th, 2020 to August 6th, 2020, showing that the area around Sumatra is starting to clear up, while Borneo has steadily become worse in sea surface salinity levels. The transport of more sediment from flood events in Borneo heading south along the coastline are causing these lower levels of sea surface salinity to occur. While on the island of Sumatra, it started to equalize back into a normal level of sea surface salinity from the riverine floods because the floodwaters were able to drain successfully through coastal wetlands, allowing for the proper mixing of fresh and brackish saline waters. This allows for less damage to the natural barriers in the coastal waters. This is a similar, my apologies again. This is a similar simulation to the sea surface salinity model. However, this one is sea surface temperature measured in Kelvin. This is data from 2016 to 2020, but I have started it here in 2018 to show the areas of sea surface temperature rise. Taking a moment to pause once the simulation rotates fully to focus purely on, here we go, the Pacific Ocean. Showing the presence of El Niño occurring off of the coastline of South America. This is causing warmer temperatures to increase around the islands of Indonesia and Papua New Guinea. Here we will show a quick overview of ENSO or El Niño Southern Oscillation, which is the equilibrium between El Niño and La Niña phases. The El Niño phase at the bottom right image of the diagram shows how the convection forces causes heavy rainfall and storm potential off of the coastline of South America, while the atmospheric pressure changes closer to the islands of Indonesia cause drought conditions and increased sea surface temperatures. Prolonged El Niño conditions promote vulnerability to natural hazards and disaster intensity for drought-prone areas in Indonesia. This will ultimately increase sea surface changes and loss of soil stabilization necessary for improving climate impact and disaster resiliency. To summarize on climate change, it's definitely more than just greenhouse gases within the atmosphere causing environmental problems. Additional mechanisms of climate change do not have to be anthropogenic, but can be worsened by anthropogenic interference. These mechanisms can be caused by natural earth processes and the release of carbon and methane deposits into the atmosphere during dry seasons of Indonesia. Sudden heavy rainfall will ultimately result in flash flooding and ground displacement as the surface stability is compromised by contaminants, fire, seismicity, and sea level rise. The potential for natural disaster frequency to increase exponentially between 2030 to 2050 is following the projections of a business-as-usual model for Indonesia's current compliance with global initiatives and lack of improvement for updating policies on disaster mitigation to include climate change impacts. Surface changes will ultimately develop due to a number of factors during wet and dry seasonal variability, and though we are reaching similar levels to the climatic optimum of the Holocene, that does not mean that we should ignore these changes that are occurring within our environment. It is important to investigate the climate change impacts in relation to natural hazards so that we can create new innovative technologies that will allow us to successfully diminish vulnerability within an at-risk population and to reduce the cost of damages and number of affected individuals during disaster-related events. This concludes part 2 of the Climate Change Impacts on Natural Hazards lecture series. Thank you for your commitment and your time during this lecture. I hope that you are able to retain the information that you need to succeed in the future and have a better understanding of how climate change has great influences on the frequency and impact of natural hazards and natural disaster events. As always, please continue to look after your health during the coronavirus COVID-19 pandemic. Wear your mask, social distance, and stay safe. I look forward to our next presentation, and I thank you again from the bottom of my heart for your attention today.